我紧张到眼镜都忘记戴。嗯。Testing 1, 2. I think the number of students getting less and less. I think the content getting harder and harder after this chapter. Huh? Okay. Okay, let's recall where we what we did last time. Okay, so we want to find limit. So how many ways we can find limit? So first way, continuous limit determine the discrete limit. Okay, so what does this mean? So if limit of a continuous function go to infinity, fx. Yeah, let me bring up the lecture. As I say something stupid. Okay, so if x go to infinity, fx equal to some limit L, and here x is in real, then we can find the discrete sequence defined by Fn, which is also equal to L. Here n is in natural number. Okay, so e.g., for example, if you look at the sequence defined by 1 over n, so it's 1/2, third, 1/3, 1/4, 1/6, 1/7, 1/8. Okay, so this sequence is going to converge to 0, because if you look at the graph of 1 over x, it decreased to 0. Okay, so you need to differentiate between continuous limit and discrete limit. All right, continuous limit and discrete limit. Okay, second, we have properties of limit of convergent sequence. Hey, is it white better or yellow better? Yellow. Yellow. Okay. Okay. White or yellow? Yellow. Okay. Huh? Try black? Nah. Okay. So yellow. Okay. So property of limit of convergent sequence says that the limit of sum, okay, or multiplication or scalar multiplication or quotient of two convergent sequence is the sum multiplication, scalar multiplication quotient of the limit of the two convergent sequences respectively. Okay? So you remember the big table we saw last time? Yeah. So I summarize in the word. What else we need? Okay, third one. Sequential limit of continuous function. Determine the limit of the sequence. And so what does this mean? So this means that if in uh, an, if you have a sequence converge to L and your function is continuous at L, then if you look at the sequence of f applied on an, okay, an is a sequence, so you apply a function to a sequence, you still get a sequence. Make sense or not? You have a sequence, and then you apply f to every number, you still get a sequence of number. So what's this number converge to? This number is just f applied to L. If f is continuous, in other words, the limit going to the function. Okay. Any questions so far? No. If not, sorry. If not, let's try and do two questions for exercise. Find limit on n over n and sorry, I think we also have one more. So it's the squeeze theorem. Of squeeze theorem. So what's squeeze theorem again? So let's say if you bound a okay, let me see. I think we have okay. So if we have a sequence squeezed by another two sequence, okay, and an, cn converge to the same limit, okay, then n also converges to the same limit. One consequence from this squeeze theorem is if you happen to know the absolute value of an converge to 0, then the original sequence converge to 0. Okay, so last time Jinghua say, hey, can we change these to some non-zero number? Huh? No, we can't because we got a counter example. The counter example is if we take our get the alternating -1 sequence. So if you look at this absolute value of this limit and then take the limit, you'll get 1 forever. Okay, but it doesn't converge. Right? Last time we saw it. Okay. So this one precisely talk about the two line you see. This two line. So I remind you the picture. It's a -1, 1, -1, 1. So if you take absolute value, it is referring to these two lines here. Yeah, but the original sequence doesn't have limit, doesn't converge. Yeah. So you cannot simply change this 0 to any non-zero number. Okay, I think we got enough. So let's try these two questions. Ln n over n and n factorial over n to the power n. Let's see if you can try it out. There are 5 methods, so see if you can use any of them. Find the limit of these two. You can discuss with your friend if you want. Discuss with your friend. Yeah, exam is like this. Give you two sequence and then ask you to find the limit. Okay, while you are doing a go around, and then I want to take attendance. Okay. Hello. Continue next part. Let's do this question first. Okay, we'll continue. Okay, so let's find ln n over n and n factorial over n to the power n. So, any idea? Any guess? Any idea? Okay, first, tell me what's the answer first, and then we will check. First one is 0. Okay. How about second one? Also 0. Okay, let's check. Okay, so first one. So you guys, I heard you guys say L'Hopital rule, right? So let's try. Huh? What? Oh, power n, yep. Huh? Because they are 0. Okay, so L'Hopital rule need to apply to the continuous function. So I replace n to be x so that we know that we are working on the continuous function. Okay. Next, you say use L'Hopital rule because ln x go to infinity when s go to infinity, x go to infinity when x go to infinity. So we can use L'Hopital rule. So we get 1 over x over 1, okay, which is limit of 1 over x, which is 0. Okay, so by method 1 just now, okay, we conclude that since we found the continuous limit of this function, then the discrete limit is also 0. Okay, is this how you solve it? Okay, so how about second one? How you solve this? How you guys find this limit is 0? What? How you find it? Check 1 by 1. How to check 1 by 1? So you check 1, 2, 3, 4, 5, 6 like that. Okay, that one is a kind of classic. But I mean, maybe you can see the pattern, but you cannot show it that way. Okay. Yeah. Any other? No, the working doesn't prove it. It doesn't prove it. I need to prove by definition. Huh? Doesn't have one word. What do you mean? Okay, so what's your what theorem or which method you use to show? Squeeze? Who use squeeze? You use squeeze theorem. So how you show it? Define two sequence. Okay, what are the two sequence? Okay, so you want to squeeze it. So how you squeeze this? Squeeze by what theorem? What sequence? 0. What will n? Okay, so I think one side is easy, right? Because you taking positive number divide by positive number is always greater or equal to 0. Okay, but why is the right hand side true? Okay, why is this right hand side true? So you need to write out what is the definition of n factorial, right? So what's n factorial? N times n minus 1, n minus 2, n minus 3, all the way up to 1. Okay, but at the bottom, how many n you have? Ah, infinite n? N, just n. N to the power n. No. For a fixed n, you only have n of them. N of them. I know, I have n of n. Yeah, n to the power n, right? Okay, we have n of them. So for example, for example, you see, if I take n equals to 2, okay, let's take 3 better. 3 over 3 to the power 3. Okay, so you have 3 times 2 times 1, and then 3 times 3 times 3. Okay, okay, okay. So what can you see? Okay, if you group your term like this, okay, you can see that the first term is n over n, which is 1. Okay, and then what? And then all the other terms in the middle, right, is less than 1. Okay, you multiply how many terms less than 1 is still less than 1. Okay, so something less than 1. So what should I put that? Let's write it as m times 1 over n, where, okay, for m less than 1. Okay, so this means what? This means this thing is less than 1 over n. Make sense or not? Make sense or not? M is less than 1. Okay, so m over n is less than 1 over n. Okay, so I give you a number, for example, 0.1 times 1 over n is less than 1 over n. Okay, now make sense? Okay, yeah. Okay, so we got this squeeze sequence, but why is it good? Because the left and right have the same limit, right? So the left hand side go to 0, the right hand side also go to 0. Okay, so since lim n infinity go to infinity of 0 is 0, also equal to the limit of 1 over n, squeeze theorem. The limit of n factorial over n to the power n is also 0. Okay, Okay, is it okay? Any question? Any question? No? Okay, so let's do some more. Okay, next, we still revision. So this concept, right, you should keep in mind and keep practicing. Okay, otherwise you will lose track. So last time we stopped at the monotonic, the theorem called monotonic convergence theorem. Monotonic sequence theorem. Okay, there's also of name, so we just fix one. Monotonic sequence theorem. Okay, but before we talk about monotonic sequence theorem, right, we should define what's monotone is. Okay, so what's monotone? Going down, okay, okay, good. So you should remember like that, but when you explain to people, right, please use the proper word. So a monotonic sequence is a sequence which is non-increasing or non-decreasing. So a monotonic sequence is a sequence which is non-increasing or non-decreasing. So next question you can ask, what do you mean by non-increasing and non-decreasing? Okay, so what do I mean by non-increasing and non-decreasing? So a sequence is non-increasing if, so what's non-increasing? It won't increase. So it either go down or stay still, go down or stay still. Okay, so how to talk about this in mathematics? So in mathematics, we will say that an is greater or equal to an plus 1 for all n. Okay, the previous term either greater or equal to the next term. Similarly, you can define for a non-decreasing sequence where an is less than or equal to an plus 1. Yeah, so you can see that these two are like just switching the inequality. Okay, just switch the inequality. So similarly, I have non-increasing. Can I define decreasing? So how do I define decreasing? Strictly decreasing. If an is greater, okay, strictly greater than an plus 1. Oh, and increasing if an is less than, strictly less than n plus 1 for all n. Okay? Okay, so now we go to another exercise. Let's do another exercise. Okay. Any question for this definition? If not, let's do two more exercise. Let's do two more exercise. So show that n over n plus 2 is increasing. And then the question is the sequence bounded? And then second, show that n over n squared plus 1 is decreasing. So if is the sequence bounded? Okay. Do you need an example first? Maybe I do one example first. Okay, let me do one example. Okay, so to show that a sequence is increasing, what's the definition? An is an plus 1. Okay, good. So we need to check if an is less than an plus 1 for all n greater than equal to 1. Okay, so in this case, our an is n over n plus 2. Okay, so n over n plus 2 is an. Is it true that this number is less than an plus 1? Which is, what's the an plus 1 term in this case? N plus 1 over n plus 1 plus 2. Okay, so is it true that n over n plus 2 is less than n plus 1 over n plus 3? Okay, is this true? So how to check if this is true? Sub value, cannot too many value you need to sub. You need to sub for every value greater or equal to 1. Okay. So what inequality? What kind of inequality? Okay, so move the function. Yeah, sure, you can move the function. So we can play around with this function. So if the top is true, if and only if the bottom is true. Okay. So we get n squared plus 3n less than n squared plus 3n plus 2. Right? Okay, good. So what can you see? So you can see that this is 0 less than 2, which is always true. So every line will be true. Because you can go from bottom to top and top to bottom. Okay, which is always true. So an is less than an plus 1 for all n greater or equal to 1. Okay. So homing, you can see we don't need to sub n. N doesn't matter here. Okay, what we need is 2 greater than 0. About that, then it's not increasing. So it's not increasing. Maybe it's decreasing in that case. But you cannot deduce increasing. Okay. So the next question is this sequence bounded? Bounded means what? Oh, I haven't recalled the definition. What's bounded? Let's recall the definition. A sequence is bounded if it is bounded above and bounded below. Okay. So the next question you should ask, what is bounded above and bounded below? Okay. Okay. Because we always need to reduce definition to some mathematical term so that we can show something, right? Okay. So we don't know what is bounded above and below now. So what is bounded below, above and below? The graph will be below the bounded. Your explanation kind of primitive, or primitive. The idea is right, but you need to use a more professional term. Okay, so a sequence is bounded above. So bounded above means your above is bounded, right? Okay, so you need to, if there exists an M in R such that every term, okay, every sequence is less than or equal to M for all terms. Okay. What did you say just now, homie? You said the graph is what? Okay, so there's a lot of unknown word, but if you put those unknown word into this setting here, you will know what he's saying. So he said the graph. What's the graph? Okay, he's saying that if you look at the constant M, right? If you draw the constant M line, okay, this line will be above of all the term in the sequence. Okay. Okay. So how about bounded below? Okay. Similarly, you can see that these idea are similar. You just swap the inequality. So a sequence is bounded below if there's another number, let's call it little m, saying it is small, such that every term is greater or equal to m, little m, for all n greater than equal to 1. Okay, bounded below, bounded. Does it make sense? Okay. So for the question just now, can you find big M or little m to bound n over n plus 2 or not? Okay. I think one of them is obvious, right? Which one is obvious? More obvious. Bounded below or above? Below. Why? What do you mean by first one? Oh, right. You're right. You're right. Because because an is increasing, right? So every other term is greater than the first term. So it's definitely bounded by a1. Okay. Because at first I thought I can bound by 0. Okay. You can do better bound. You use a1. Okay. Use a1. So that's right, huh? Yeah. I think, no. For every increasing one you can, or non-decreasing one. Right? Then if you your favorite damping, your favorite damping, yeah. Okay. Under above, yeah. Can be a bound. Can be a bound. Yeah. Can be a bound for every increasing, for every monotonic. Yeah, correct. Yeah, good. Yeah, correct. Yeah, that's right. That's right. Okay, so let's go back to just now, the question just now. Okay, since let me wait. Okay, since we know that n over n plus 2 is increasing. Okay, in particular, what? In particular, A1 is less than an for all n greater than 1. I think we know that we get a1 is, sorry, we get an is bounded below by a1. Below by a1. Below by a1. Can you see that this, like, okay, you see here we got equal sign, right? Here we only have strictly less than. Does it matter? Matter, ah? Why change your stand? Why doesn't matter? Why matter? This is less than or equal to. Okay, it's or. You don't need to satisfy both. Okay, you satisfy equal or you satisfy or less than. That's enough. Okay, because this is less than or equal to. Yeah, less than or equal to. Yeah. Okay. It's an or. So one of them is true, then it is true. Right? Oh, you guys haven't learned discriminant. Or, but you see or before? Sorry, I'm asking stupid questions. Or, so P or Q, right? If P true or Q true, then P or Q is true. Yeah. Yeah, mathematical reasoning, yeah. That's right. Okay, how about, is it bounded above? Huh? We already proved that it's bounded below, right? Is it bounded above? Why? Oh, yeah, correct. Okay, so is it bounded above? The question is. Actually, we haven't found A1, right? What is A1? 1/3. Okay, good. So you keep increasing, and then you say that at infinity, it bound by that infinity thing. Okay. So what's that thing? Okay, do limit. Okay, let's do limit. Let's see, because you keep increasing, right? Okay, you keep increasing. Okay. So if it approach a number, then it will be bounded by that number. If it's infinity, then unbounded. Oh, unbounded. Yeah. Can ma, right? Unbounded. So let's see if it is bounded or not. So let's compute n infinity of n over n plus 2. So what's this? How to compute the limit? You can divide by 1 over n. Hey, who is this? 1 over 2 over n. Okay. So so these are the combination of convergent sequence. So you can use the property of convergent sequence, right? So this you can see that this number here as a constant sequence. So this constant sequence converge to 1. This constant sequence converge to 1. This sequence converge to 0. Okay, so you can split the limit out by method. I forget which method already. I think that method 3 just now I mentioned. Okay, you can only split. So I want to remind you again, or warn you again. You only can split your limit when all the sequence are convergent. Okay. in this case, we know all of them are convergent, right? So 1 is a constant sequence. 2 over n converge to 0. So we can split the limit up. So this is just 1 over 1 plus 0, which is 1. Okay? Okay, so this implies what? This implies that 1 over 3 is less than an is less than 1. Okay? Correct or not? No one have a suspicious. Above, bounded below by 0. You also can make it bounded by 0, but I would say that 1/3 is a better bound. It's a better bound. You can bound it by 0, but 1/3 is a better bound, right? Yeah, both. It can be bounded below by 1/3 and 0. But I mean, 1/3 will be a better bound, right? Because you are closer to your sequence. Oh, yeah, sure. Negative infinity is false. Why? Because negative infinity is not a real number. We want to bound by a real number. So if you say I can bound it by -1, -2, -3, that those are also true in this case. I mean, but yeah, negative infinity or infinity cannot work. That's why we say unbounded just now. Yeah. Okay. Yeah. No one want to challenge why an is less than 1. Is it? Okay. If you believe, then we can close place because uh believe. Yeah. If you don't believe, then we need to go something deeper. But anyway. Okay, so an is less than 1. So hence the sequence is bounded. Okay. So any problem with this question here? Yeah. Yes. Yes. And so I have to same time. Or anytime, anyone. And have to be both. Okay. Okay, maybe we take a break. So we come back 907.如果这样子，
这样子写的话，然后我讲，就是我这样写，如果我讲 m 小过1的话，这样它不是不可能等于1/2，我知道它来。
哦呀
我要讲，
可以哦，因为像我们刚才说，哦嘛，你一个对就可以了，一个对一个错还是对的
啊，
是啊，
有哦，
不，那个 less than or equal 吗？这个符号？
可是从这里，如果我这样子写，
对，
然后 m 小过1的话，就是代表了它没有一次是等于这个right，
对，
所以我要讲
对，你讲的这个东西全部没有错，但是我想讲的是这个东西，你对这个理解，这个东西是 less than or equal to，OK，所以这个东西是 less than or equal to 是对的吗？因为它 less than 它嘛，它虽然不 equal 它也不用紧，我只要其中一个对就可以了。P or
Q 一定要 equal。
没有，也是 less than，也是 less than or equal。
就它要有，
它可以偶尔 less than 一下，偶尔 equal 一下，偶尔 less than 一下这样。
如果我这样子写right，就从这边看代表有一次。
对，
来讲来 equal when
不用，你比如说这个，我可以这样写的，比如说这句话是对的，我可以这样写，这句话是对的啊，它不等于对不对？但是它小于嘛，但是这句话是 less than or equal 嘛，这个只是一个mathematical reasoning 的东西啊，就是 P or Q 吧，就是它其中一个对就是对啊。
我这样子写，正好不要2小过3个哎。
嗯，
有 one instance 它是 equal，不然它不能讲哎，因为
没有这样，真的没有这样，真的没有，它可以 squeeze 到很死的那种。
是嘞，我的 theorem 是嘞，0小过等于 n 小过0，这样子就不能看小哎。
没有嘞，我没有讲的话，我就感觉不 make sense， 哪里不 make sense？OK， 对啊，这个不 make sense 跟这个没有关系。
可是
因为这个不 make sense 跟这个没有关系。
我它只是 less than 吧，就它是 less than or equal。
你如果真的很想要，你就写 less than 就好，也可以。为什么不 make sense？
因为你 squeeze Q 要等于
OK， 这样还是那个问题，就是说它等于就是 OK， 等一下 P or Q is true if or Q is
我说这个就是
其中一个对它就对了。这句话我说这句话对，其中一个对就对，另外一个错不用紧。是，这个是那个这个的定义，这个 or 的定义。
没有，可是嘞，如果我这样子理解right，它其实，let's say 我讲 P 是 less than，这样 P true 吧，Q 是 not true 的，这样他就讲它是 less than 吧，不是 equal。但如果这个是0，这个是0 ，n 只是可以 less than 0，可是这边讲 0是等于 n。
对，你看，OK，用你的例子，所以你现在要问这句话对不对嘛，对不对 ？OK， 假设啦，这边有两个情况哦 ，case 1跟 case 2哦 ，OK， 假设 n 大于0，它就不可能小于0啊，所以这句话是错的。如果 n 等于0的话，你要知道的，每一个号码不可以小于自己，所以这句话也是错的。所以其中一个对的，它都是错的。就这样哦。
我觉得
什么？没有，你要记得一个重点，就是 P or Q 这整句话要对的话，其中一个对就可以了。这个是这个 P or Q 的意思，可以吗？没有讲一个错啊，这句话就错的。如果是这样的话，那个是 P and Q。P and Q 的话就这样，这是 P and Q 跟 P or Q 的差别。P and Q 就是说，如果你 P 对 Q 错，这样子这句话是错，这样就不可以了。哦，是可以的。没有问题是。
那个 squeeze theorem right，
对
A 小过等于 B 小过等于 C，
对
这个一定是要小过等于 right， 这不能是 B 小过 C，A 小过等于
可以，它可以被 squeeze 到很中间的，它不用有时候等于一下的，它可以被 squeeze 到中间。你明白吗？
可是我们通常找那个 limit A limit A
小过等于小过
B 等于0，
就是0
小过等于0 right。
对
m
所以
如果
大过等于0
我们这样子
或
讲，
小过0，
就是0小过等于 B 小过 C 这样。
但是你要想哦，你就要想上次我讲的一个问题，就是你如果 limit 去0，不是你的 term 不一定会 hit 到0的，你可能是很靠近0罢了，你不一定要 hit 到0的。
所以就讲我不能讲
这个 m
不，
乘以 m
你一定要记得有一个观念，就是 limit 去到0，不是你不一定要等于它的，你可以无穷靠近它，
那 m 是什么？
但是你不用靠近它。 哎，不，你不要等于它，你记得吗？就是你很靠近它，但是你摸不到它，对不对？所以他们两个都可以很靠近，可能一个比一个更靠近，但是他们两个人都摸不到零啊，可以吗？
可是这里有的等于的。
什么？
至于如果
如果你要很
如
precise，
果
你
n 是1的话，就没有。我问题是来，如果我这样子写啊，就代表它没有等于的。可是如果我要写超过等于，我需不需要来讲哦？
几十等于不用，因为就算它错，我也可以这样写啊。我就算错，我也可以这样写啊。但是如果你要 precise 的话，你就写小于咯。但有时候写小于等于有好处啊，有时候的。
那你怎样知道我是小于还是小于等于的意思？
我只要小于，我就可以写小于等于，我可以一大堆错的东西啊啊。
问你们问题，我知道这样子是 more precise 的，对不对？但是我当时做的时候，我没有想那么多，我就直接把它展成这样形式。然后因为这个像 limit 等于0的话，就你不能中间不对的，你就直接写了等于0。
有点草率，
我知道，但是你不能说它是错的。
不能给满分。
哦，好，对不起，我会更
只有
规范的。
因为这个没有步骤，这个只是一个概念。
是的，是的，是
对
的。然后还有一个就是概念，就是您刚刚说，对，这是0，对不对？然后你说是中间是每一项都是小于1的，每
对
一，项都小于1吗？
当然咯。
好，然后老师就是这个 limit 呀，就是你这个 limit n，你取无限的时候，这个是不是1呢？对吧？
limit 是1，但是
所以你要
它本身。
严谨一点哦，你要 precise 一点。
我想想，我想想。哦，我想想。
没有，
哦，我知道了，我知道你用另外一个方法，你用那个 property of limit of convergence sequence。
没有啊，
什么没有？
不是，我就是说，我就是很好奇，因为你说中间每一项都小于1，但是事实证明，就当的
你是
n
说
取
limit 呀？你说的是
对对对
limit，
我说
我没有
limit
取 limit，
你说的是
所以
什么
你是另外一个方法，你是用那个 property of
你就
limit，
直接说，
你是用
这
那个 convergence 的 sequence 全部把它乘在一起，
对对对对对，
然后你就是
我
一乘一乘一乘一乘零啊。
对对
OK，好，这个很好。
哦对，所以
OK，
就是
再好说一说。
没有什么，对，所以就是如果不是limit的话，这个确实是小于1的，对不
对
对？
对对对对，
谢谢老师。
好，可以，很好。
就是之前你是不是就是
你还是他？
没有问题？我很快我就一下就好。就是你之前好像是不是写过一个，就是
我要开始。
就是这个，
Yeah
是这个什么意思？
这个就是那一整个图表的意思，我把它 summarize 下来了。你还记得我写的东西吗？吗？
不代表会等于。
这个就是你看一下，刚这样子哦，对，你给一个 value 出来了，
其实还有很快我看得了。
你就出现
这个我用手写的上次，就是sorry
没有
sorry，
哦
手写
，OK，
这个，我 summarize
这个
啊，就是你可以
就是必须要收敛才可以。
呀收敛。
第10道题，2题、3题、4题，这题有人做不完哦，1个小时吧，你给。
实体当然是不会很长的咯。The step，
是线下
等于
实体
第3，下礼拜不是啊？礼拜2不是啊？
下礼拜
要不然迟到哦，
这个
让我坐后面一点哦
必。须要收敛才可以，这样才可以用。
对，
对它不会
对，没有错
谢。老师。
来，最后来快，你要开始了。
就是我那有一个很奇怪，我不是很理解的点啊，有等于错不我的 AN 是这个嘛？我的 AN 加1 actually 是这个东西，
错了，他
我全部加一个
这
东西。
个没有等于，因为他是小过零，
其实是矛盾的，因为它没有去一个 conversion 点，是不是？因为我们的包的一定是一个红的，就我不是很理解这个。
这个
因为这个是对的，因为它绝对 convert 是这个点，它永远在这个里面。但如果它在这个，它绝对是 false，因为它永远会这个。
这就是 and right，
我们是2个平行的那个什么，like always。
啊，我知道了，我知道了，因为我们只是一个点罢了，我们不把它看成 function，
哦，如果
我们看点罢了，因为是 discrete sequence，虽然每一个
不大同道理。
啊，我觉得你在看错的东西，我们是看这一个号码，我们是看一个真正的号码，
啊
我们不是把 an 看成跟 an 加1，我们不把这个看成不同的 function，那个是另外一个层次的东西啊。
是方向嘛，然后我就开始去
我知道，我知道，我知道，我知道，但是我们不看 function，我们看的是 number，看 number 会出来。
拿 this 点，
对对对对，我要把 n 放进去看那个号码出来。虽然我们在讨论 a 加 an 的时候，不是，其实每一个 an 跟 an 加1都是一个号码来的啊。但是如果你把 an 加1看成一个 n 的 function 的话，它就是一个 function，那是不同的东西，不一样的东西，这样。
其实 a n 转的里面就可能我就找这个点，还
啊
有，跟这个点跟这个点，对啊，如果我在一个这个点，然后这个
感觉他们活在不同的线，你应该是在 n 的那边找到一个点，在 n 加1那边找到一个点，这样。然后这一些点不是会被这条线绑的。如果这个东西 increasing，OK，如果是我们刚才那个 example，可以吗？
这个点是不是都大过哈？连这个不会拎成一个 discrete，
所以呢，我们 show 了它的 limit，它 limit 到一个点，刚才
为什么这个点啊，它会
会大于会小于会 bound 它们，是不是？
很难 convert。
这个是一个比较难的课题，我可以回答你，但是他们
OK
好像没有兴趣，但是我可以回答你。
我再有个问题哦，
嗯
都是从natural number 嘛，所以我可以 guess 就是有，然后我们很多是用 fx 去 prove 了，that's why 有 fn。
啊，对对对对对，
可不可以写 fn 直接？来，因为题目它直接给 fn 嘛，如果我 treat n as a unknown number 吧，就是 natural number。
那你要写咯，你要写你这个 n 是 real number，哦，这个 n 是 natural number，这样就很乱了。所以通常我们就换 notation 哦，所以我们就知道 x 的话就是 real number，n 的话就是 discrete 哦，不然你又要用同一个符号讲不同的东西，这样就有点乱。
什么时候都用 fx？
什么时候要用 fx？
Like all the time 嘛。
如果你要算 continuous function，你就要用 fx；如果你要算 discrete，你就用 fx。
那里面什么 discrete 嘛？
对，但是因为就像你讲，我们有时候要算的时候，我们要透过 fx 嘛，所以那时候就要用 fx 哦。算好 fx 的过后，然后回来讲 fx。
我们只写 fx 就行。
不行，
OK。
不行，为什么不行？
因为还是 discrete。
对，
好
对，你知道 ，OK， 我知道你知道。每次问我你知道的东西 ，OK， 来 ，Let's start。Okay, just now we use squeeze theorem to prove. Okay, just now we use squeeze theorem to prove that n factorial over n to the power n is convergent to 0, right? Okay. So apparently, Jinghua got another method. Don't insult you. Why am I insulting you? Okay. Okay, so method 2. Okay, method B. Okay, method B will use properties of. Okay, hello. Same question. Convergent sequence. Okay, let's recap what we did just now. So we want to find the limit of n infinity of n factorial over n to the power n. Okay. So we realize that we can split this into multiplication of different sequence, right? Let's see what we are doing. So many one. Yeah, so many n, correct. So in your mind, right? In your mind, you should fix this n. Okay, in your mind, you should fix this n. Fix this n as 3 just now. So we got 3 terms, 3, 2, 1, then bottom 3, 3, 3. And then you can fix this n with 4, 4, 3, 2, 1, and then divide by 4, 4, 4, 4. Okay, then you generalize this. Okay, continue. So just now we split by, because at the top you have n terms, at the bottom you also have n terms, right? So you can group the terms one by one. Okay. So what do you see? Okay, if you regard this n bracket here as n sequences, you can see that all of them are convergent sequence, right? Okay, so first one you get what? First one is easy. You get 1. Okay. The next one maybe a bit harder. N minus 1 over n. What's this? N over 2 over n. And then maybe you get 2 over n. 1 over n, these are easy, right? 2 over n, 1 over n, 3 over n, 4 over n, these we know. But what is n over n minus 1 over n? We can do the trick again. We divide by n, where we get 1 over n over 1. And then 1 over 2 over n over 1. And then keep going. Okay? And then you can see, what can you see? So this, the first term converge to 1. Second term converge to 1. Converge to 1. And then the other converge to 0. Okay? So they are all convergent subsequence, convergent sequence. So you can split the limit of multiplication of convergent sequence is the multiplication of limit of convergence sequence. So you can split the limit. So 1 times 1 times 1 times 0 times 0 times 0 times 0, you get 0. Okay, so we can split the limit because it's all convergent, multiplication of convergent sequence, so we can split the limit. Okay, so okay, so you might get, depend on how you write the sequence down, you will get how many 0. Something. Either 1 or 0. Okay, so the conclusion is the limit here either 1 or 0, and then the last one must be 0. So you can conclude that this is 0. Okay, the last one must be 0. And then in the middle, you will get either 1 or 0, depend on what you get. Depend how you write the equation, the sequence down. Okay. See. Okay, so close this case. So let's do exercise just now. And okay, just now Chiro asked, so if you have an increasing sequence, right? And then you increase, keep increasing, and then you say that it limits to a number 1. Okay, why this 1 necessarily greater than an? Okay, let's say you have some term above 1. Okay, let's say you have some terms above 1. Okay, but not that okay, above 1 means what? It is strictly okay. So suppose for contradiction, an is strictly greater than 1. Okay, if it is strictly greater than 1 means what? Then you have terms that are far away from 1. In that case, 1 cannot be the limit anymore. Yeah, you need to understand this. So if you have far term that is greater than 1, then the next following term also greater than 1, right? Because because it is increasing. So your AN will keep increasing or equal. Okay, but this number is greater than 1. There's a fixed distance from 1. Okay. So let's say for n greater than m, then 1 cannot be, okay, then 1 couldn't be the limit of 1, of an. Okay, you need to think about this sentence. This sentence is correct, but you need to think about it. So if you have a term greater than 1, then all of the term after that also greater than 1, because it's increasing. Then 1 cannot be the limit anymore, because you cannot be arbitrarily close to 1. Okay, you must have at least a distance am minus 1. You need to think about this. What I say is correct. You need to listen what I say and then think about it. What I say is correct, so you need to make sense of what I say. Okay, you will have a distance am minus 1, so you cannot be arbitrarily close to 1 anymore. So 1 is not the limit if it is not bounded by 1. Okay, so it is the increasing that help you to get to 1. Otherwise, you cannot get to 1. Very good. Very good. That's right. That's right. That's right. Very good. That's right. That's right. Okay. Why you cannot find equal to 1? Actually, you need to solve this, you know. You need to solve this. So suppose n over m plus 2 is equal to 1, right? N is equal to m plus 2. So 0 is equal to 2. So this is a bullshit. So it's a contradiction. language. So well, in a proper maths textbook, they will say this is absurd, and absurd, stupid. Okay. So there's a contradiction here. So there's no n that you can achieve 1. Okay. So this idea is very important. This limit idea is very important. You can be as close as possible to a number, but you can never reach that number. And this idea is really important.
One of it. Saying true, right?
Yes, correct.
But both equal also true, right? Because 1 will be always less than 1, right? So the statement of less is true, so it's always true.
Oh yeah, sure. Yeah. You want to put less than equal also true, but if I put less than, I'll be more precise. I want to tell you. So that's me. Okay. So that's why I want to tell you. Whatever we write, right, we have a meaning one. There's a reason why we write like that. So if I write strictly less than 1, I want to tell you, I cannot reach 1. Okay. If I just say this is less than equal to, I don't really care whether it is equal or not. This is the attitude we adopt here. You get what I mean? Okay. Sometimes if I say strictly equal to, then that's me. I want to tell you, you can never get 1. You will get this contradiction. Okay. Sometimes I don't really care if it equals or not. Less than equal, that doesn't mind. Either one of them is true. I'm happy. So I put less than or equal to. So there's some attitude behind this writing. Actually, everything works like this one. Everything in this world. Yeah, when you read the textbook or what, because you can see that one technique or one skill in different textbook they write differently. Actually, that's the attitude by that person. Yeah. So depend on what you want to convey, you will write it different. Or depend on what you want to achieve, you will write differently. Okay. Okay, so let's continue with this second example. So I will let you try first. I'll let you try. So just now we show that n over n plus 2 is increasing, right? Now you try and show n over n squared plus 1 is decreasing. And then see if you can find whether this sequence is bounded or not. Okay. Just now we do one direction increasing. Now I let you try the other direction decreasing.
来找我，这老师要去找你的，来个整过去，来这是借我。我以后你都这样，他会来。哇，这个好可怜，靠背啊，这个，然后我讲好迷。啊，这个。不要去那种他，那个一拍，对，就是还有。啊，也呀，除了看可以。还笑吗？apa? Atau mana? Yang ini kalau sejarah. Ah. 这是没有，我的领导是
Hello, testing. Okay, so you working on it or already done? No? Okay, this question like show that, right? If it show that, you just go and look for this definition and then try and show it. Some question will ask, determine whether this sequence is increasing or decreasing. Then you need to try, right? To try different inequality, right? Do you get what I mean? So if this question says show that, okay, show that, then you just go and show it. Just go and look for decreasing. If you need to determine, then you need to try. You need to test both inequality. Less than equal to or greater or equal to. Right? Okay. Okay, to show it is decreasing, right? What do you need to do? You need to show sequence is decreasing. We need to check an is greater or equal, or greater or less than. Greater than an plus 1 for all n greater to 1. Okay, so let's check it. So how to determine whether this is true or not? Okay, so similarly, you can multiply across the denominator. Okay, so do we want to multiply up? Yes, sir. Make sure, maybe we don't want to do too many expansion. Let's do just enough expansion, okay? So what do I mean by just enough expansion? You have an n square term on left hand side. Maybe we build a n square term on the left hand side. So we get n square plus 2n plus 1 plus 1. Okay. And then can we okay, so we can do a bit further simplification. So we get n times n squared plus 1 plus n times 2n plus 1, which is greater than 2n plus 1, n squared plus 1. Right? Okay, so what can we do? You can see that here we got n over n squared plus 1. Here we also have n times n squared plus 1. Is it following? Okay, maybe I expand it further. Hey, hello. Just start already. Okay, so you can see that there's two similar terms we can cancel. Okay, which is 2n squared plus greater than n squared plus 1. Okay, so in the end we get n squared plus n greater than 1. Okay, is this true? Why? Okay, good. So because n is greater than 1, so n squared plus n is always greater than 1. Which is true since n is greater than 1. Okay, so how about bounded? Is it bounded? which one is easier to see? Order above. Okay, good. So n over n squared plus 1 is bounded above. Why? You need to find me a n. Okay. Since let me define this as an first. So the an is bounded above since an is less than or equal to a1 for all n greater than 1. What is a1? a1 is 1 over 2. Okay. As an is decreasing. Is it bounded above or not? Bounded below or not? Yes. So how you show it? You limit. Okay, so let's try limit. Let's see what happened at the far place. So n over n squared plus 1. How do you find the limit? Divide by n squared. Okay. I think it's a good choice. So you divide by n squared. So you get 1 over n over 1 over 1 over n squared. Okay. So how to compute the limit? Because this is a combination of convergent sequence. So you can bring the limit into all the terms. Okay. Which is 0 over 1 plus 0, which is 0. Okay. So by the similar argument with increasing sequence, we see that we see that an is greater or equal to 0 and greater is less than half. Less than or equal to half. And strictly greater than 0. Is it strictly greater than 0? Yeah. Okay. Strictly equal to 0 because n can never be 0. Okay, so it's strictly equal to 0. So the sequence n over n squared plus 1 is bounded. Okay. Any question? No question? Qingrou got question? No question. Okay. No, don't be afraid. Just ask. Okay, so you don't realize actually you do 2 examples for the monotonic sequence theorem. Okay, you already showed this. Okay. Monotonic sequence theorem. See. Huh? Too fast? Maybe. I don't know. I know. But I don't know whether I'm slowing down or not. Am I very slow down? Okay. But I mean, okay. This topic is worth to slow down because this topic there's a lot of tests you need to take in. So I need to make you every day repeat. Yeah, just repeat. Keep repeating. Okay, repeat. Do the same thing. Because the other class kind of cannot digest. So this topic kind of very long, and then there's a lot of tests. Okay, so continue. Let's continue. Okay, so let's remind the statement of monotonic sequence theorem again. Okay. Every bounded monotonic sequence is convergent. Sequence. Okay, last time we talked about this sequence. Okay, still, I want to remind you the concept of limit. So limit doesn't mean you achieve the number. It can get arbitrarily close, but you can never reach the number. Okay, you can never reach it. Okay, but you are very close to it. Very close. Okay, so this is the idea of limit. Okay, so example, Example. So one question is suppose you know that AN is increasing. Okay. And every term of AN bound by 1/3 and bound by 1/3 and 1. Okay. So explain why the sequence has a limit. Okay. And then what you can say about limit. Okay. Okay, so why? How about I pick name? But in 林天阳 Where's 林天阳 林天阳 Oh, okay. 来，林天阳。Hello. Listen to what your friend said. You don't understand the question? What does it exactly mean? Okay. So do you know what does sequence increasing mean? Okay. And then do you know what does it mean by n less than equal to 1 and less than equal to 1? Okay, you know that. So explain why the sequence has a limit. Do you know what does the sequence has a limit mean? Okay, so why does it has a limit? It is bounded, okay. So why bounded imply convergent? Does it enough to deduce convergence from boundedness? It is what? Monotonic. Okay. So since it is monotonic and bounded, it satisfies the theorem. Okay, so the theorem saying it is convergent. Okay, so one key point here. If I take away monotonic, the bounded sequence might not be convergent. If I take away boundedness, monotonic sequence might not be converged. Okay, let's see this example. I think this one is helpful. So bounded sequence doesn't necessarily converge. Can you give an example? I think we see this example before. Sin x. Sin x. -1 power n is the easiest one, right? Yeah. Not say cannot, but you need to check first. I mean, there's an easier example, right? Easier example we saw -1, 1, -1, 1, -1. I know. I mean, you need to check first. Okay. So this one is the easiest one, right? Bounded by 1 and -1 every term. But there's no limit. How about monotonic but not bounded? Doesn't necessarily converge. What natural sequence? Ooh, good. Hey, do you want to come to max degree? Please switch to max degree. We need people. Okay, so if you take an equals to n, okay, so this is an increasing sequence but not bounded. So you keep increasing 1, 2, 3, 4, 5, and then keep increasing. Okay, so it's not. So you cannot simply take away the condition. So in the theorem, it's very important. You need to satisfy every theorem and then you will get the result you want. Okay? Okay, so by monotonic convergence sequence, you get the limit. So what can you say about limit? Can you say something about limit? If all your term is in between 1/3 and 1. Can you say about the limit? Your an is increasing, okay? Keep increasing. And then it is bounded below by 1/3, bounded above by 1. It has a limit because of monotonic sequence theorem. So can you say something about limit? Recall what we did just now. We show that some sequence is increasing, and then we show it is bounded below, and then bounded above, we go and find the limit, right? Huh? Uh-huh. 1 or 1/3. So the question is 1 or 1/3. Increasing, right? Strictly increasing. Okay. So you cannot. Okay, first of all, the limit must lie in between 1/3 and 1. Okay, this one clear, right? So because this is strictly increasing. Okay, strictly increasing. So it must be very far away from 1/3. Right? Yeah. Alright. But bounded by 1. So I think the limit is equal to 1. 1. Equal to 1, I think. Oh, less than or equal to 1. Yeah, less than or equal to 1. Okay, less than or equal to 1. Okay. Yeah, limit. Less than or equal to 1. Right? Maybe it can be increasing, keep approaching 0. Also can, right? You get what I mean? So if I draw this curve here, increasing, maybe it approached 0. It approached 0. Okay. But maybe 1, and maybe 1 is at the top here. Okay. So we only can say that the limit is less than or equal to 1. No. What?
shows that an can be equal.
Oh, can be equal. Yeah, can be equal. So that's mean I say less than or equal to, not strictly less than. Right. So this an can be just less than 1 or sometimes equal to. Yeah. So if it is less than 1, it still satisfies this equation here. Inequality here. Okay. It's the P or Q business, right? Yeah. Okay, so what you can deduce is maybe a bit. So what can you deduce is the limit of an is less than or equal to 1 and greater or equal to 1/3. Okay, this is what you can deduce. Actually, you can compare this with the squeeze theorem, right? Okay, you think of 1/3 and 1 as two constant sequence, right? But they converge to different number in this case, right? Squeeze theorem need to converge to one number, but this converge to two different number. And then one condition is an is monotone. Okay, then you converge. Yes. No. Okay. I mean, okay. Again, and again. Okay. So if I like, I can remove equal. Yeah. So yeah. Okay. Okay. Why can it can. Who can approach zero? You mean the sequence, right? Yeah, you can. I just says that the limit is less than or equal to 1. So if it is equal to 0, then 0 is still less than or equal to 1. Huh? Seng, huh? Larger than 1. Oh, sorry. I should pick something greater than 1/3. So I should pick over 3. Yeah, pick 2/3. Yeah, let's pick 2/3. Yeah.
Be bounded below by.
Bounded below.
So you have to go like that, right?
Like what?
Because n is bigger than bigger or equal than 1.
At 1/8.
Not necessary.
But it's bounded.
Bounded, you still can just take in point. Yeah. You just take point by point. Yeah, I can start from there. Yeah, I can start from there. Okay. Actually, I don't want to put a 2/3 here. Here, actually, this number here should depend on your first term. Okay, this first term is greater than is a m that is greater than a1, less than or equal to 1. Okay, this one better, more precise. If your first term is 2/3, then this example wouldn't work again. So I would say depend on your sequence, which one is your A1, then you can create a sequence that is satisfy this condition. Yeah. Okay. We spent another lecture talking about same thing. Never mind. Next time we will go into series. Huh? Next what? Still 6 minutes. Okay. I mean, the next one we have a long question. Do you guys want to continue or 6 minutes only? Yeah. Huh? Last question. I mean, this is the last example. Then next week we go to series. Go on. Okay. You guys don't have class, is it? Next time. Next. Huh? Huh? Not a schedule. Okay. It's okay. Huh? Okay. I just left it as a homework. So I left it as homework. This example kind of long. Yeah. So left it as homework. So left as homework. So show that the sequence. Show that the sequence AN defined by A1 equals to 2, AN plus 1 equals to AN plus 6 over 2 for n greater than or equal to 1 is convergent. And try to find this limit. Okay, first of all, do you have any question? If you understand this question, then we can leave. So this sequence is defined recursively. Okay, and then you want to prove that this is convergent. And then try and find this limit. I think you cannot use property of limit of convergent sequence anymore because you don't know whether AN converge or not. Okay, so you don't have those two, and you don't have function for now. I'm not sure if you can write out another formula for n, explicit formula. Maybe you can. Okay, in my class, the other class that make it, they use another method to show this. So you actually can find an n formula for this. Meaning you can find the formula for AN. Okay, you can do it if you want. Otherwise, maybe you need to use the theorem. Okay. You try. 2 some of them is not useful. I think most useful is squeeze and this monotonic convergence. The other you don't have condition, right? You don't have enough. Unless you can squeeze, I think very hard to squeeze it. I'm not sure. Maybe you can squeeze, but 2A1 term. 2A1 terms, what do you mean?
One is 2. Is
2 plus 6 over 2. Hey, sorry, shouldn't be equal. So here put equal. Yeah, huh? A1 is 2. A2 is A1 plus 6 over 2. So 2 plus 6 over 2. So it's 4. And then the A3 is A2 plus 6 over 2. So it's 4 plus 6 over 2. So it's 5. I can understand this sequence or not. So you can list it. A1 is 2. A2 is 2 plus 6 over 2, which is 4. A3 is 4 plus 6 over 2, which is 5. And then you keep going. So 5.5, and then you keep going. Yeah, converge to what? You want to guess first? No lah, because you already have 5.5. How can convert to 5? Must be something greater. Yeah, try and show this converge to 6. Yeah, try show that this converge to 6. Okay. Okay. Everyone got this question already? Okay. Yeah, try. Try first. Yes, if your friends sick or what any reason, ask them to email me. Then email me why they have stuff.
太原显的是
Okay. Yeah, thank you very much. See you next time.